Determining the correct size for the neutral conductor in a wood drying system is crucial for safety and proper operation. The wood drying system uses 230-volt motors, but also incorporates 115-volt convenience outlets. The initial step involves calculating the total amperage draw of the motors. To calculate the amperage draw of each motor, use the formula amps equals watts divided by volts. Once you determine the amperage for each motor, add them together to find the total motor amperage. The second step involves calculating the neutral amperage. In a perfectly balanced system where all motors draw the same current, the neutral current would be zero. However, the presence of 115-volt convenience outlets creates an unbalanced load, necessitating a neutral conductor that can handle the resulting current. To estimate the neutral amperage, use the formula neutral amps equals the largest motor amps multiplied by 2/3. The third step focuses on sizing the neutral conductor. The neutral wire must be capable of safely carrying the calculated neutral amperage. According to the National Electrical Code, NEC, the minimum neutral size for a 100 amp service is 50 amps. However, it is generally recommended to size the neutral for at least 75% of the phase current to enhance safety and reliability. For example, consider a system with two 230-volt motors, each drawing 25 amps. The amperage draw per motor is 25 amps. The total amperage draw for both motors is 25 amps times 2, equaling 50 amps. The neutral amperage calculation is 25 amps, which is the largest motor amps, multiplied by 2/3, resulting in 16.67 amps. Based on this calculation, a 50 amp neutral would meet the minimum requirement. However, it is recommended to upgrade to a 75 amp neutral to provide an increased margin of safety and improve the system's overall reliability. This approach to neutral sizing ensures that the system can handle potential imbalances and fluctuations in the load, contributing to a safer and more dependable wood drying process. Consider the scenario where multiple motors are connected, each with varying horsepower and voltage requirements. If you have one motor that draws 20 amps, a second that draws 30 amps, and a third that draws 15 amps, begin by adding these values. This totals 65 amps. Then, if you have a lighting load of 10 amps and convenience outlets that could potentially draw another 15 amps, you need to consider these loads as well. This brings the potential total load to 90 amps. The NEC provides guidelines for sizing conductors based on the anticipated load and specific application. For motor circuits, the code typically requires conductors to be rated for at least 125% of the motor's full load current to account for starting currents and potential overloads. Therefore, you must consider the highest motor load and apply this factor. For continuous loads, which are loads that operate for 3 hours or more, the NEC requires conductors to be rated for at least 125% of the continuous load. For example, if the continuous load is 50 amps, the conductor must be rated for at least 62.5 amps. To determine the appropriate wire gauge, consult NEC Table 310.15b16 or a similar table that specifies the ampacity of conductors based on their insulation type and temperature rating. Select a wire gauge that has an ampacity equal to or greater than the calculated load. For example, if the calculated load is 60 amps and you are using a conductor with a temperature rating of 75 degrees Celsius, you might choose a number 6 American wire gauge, OG, copper conductor, which typically has an ampacity of 65 amps. Voltage drop is an important consideration, especially for long wire runs. Excessive voltage drop can cause equipment to malfunction and reduce the efficiency of the system. The NEC recommends limiting voltage drop to no more than 5% for feeders and 3% for branch circuits. To calculate voltage drop, use the formula voltage drop equals 2 times K times I times D divided by Cm, where K is a constant representing the conductor material, I is the current in amps, D is the one-way distance in feet, and Cm is the circular mils of the conductor. If the calculated voltage drop exceeds the recommended limits, increase the wire gauge to reduce the resistance and minimize voltage drop. Grounding and bonding are essential for safety and to prevent electrical shock hazards. The grounding system provides a low-impedance path for fault current to return to the source, allowing the overcurrent protection devices, such as circuit breakers or fuses, to quickly clear the fault. Grounding refers to connecting the neutral conductor to earth at the service entrance. Bonding refers to connecting all non-current carrying metal parts of the electrical system together to create an equipotential plane. The size of the grounding and bonding conductors must comply with the NEC requirements. Typically, the size of the grounding electrode conductor is based on the size of the service entrance conductors, as specified in NEC Table 250.66. Bonding conductors are sized based on the size of the circuit conductors, as specified in NEC Table 250.102 cone. Overcurrent protection is necessary to protect the conductors and equipment from overloads and short circuits. Circuit breakers and fuses are the most common types of overcurrent protection devices. Circuit breakers are resettable devices that trip open the circuit when an overcurrent condition is detected. Fuses are one-time use devices that melt and open the circuit when an overcurrent condition occurs. The size of the overcurrent protection device should be matched to the ampacity of the conductors it is protecting. The NEC specifies the maximum overcurrent protection allowed for different conductor sizes in NEC Table 310.15b16. For motor circuits, the overcurrent protection device must be sized to protect the motor from overload, but it must also allow the motor to start without tripping. The NEC provides specific rules for sizing motor overcurrent protection in NEC Section 430. Branch circuits are the circuits that extend from the panel board to the point of use, such as lighting fixtures, receptacles, and equipment. Each branch circuit must be protected by an overcurrent protection device, and the conductors must be sized to carry the load served by the branch circuit. The NEC specifies the minimum size conductors and the maximum overcurrent protection allowed for different types of branch circuits. For example, a 15-amp branch circuit typically uses number 14 AWG conductors and is protected by a 15-amp circuit breaker or fuse. A 20-amp branch circuit typically uses number 12 AWG conductors and is protected by a 20-amp circuit breaker or fuse. Electrical panels, also known as panel boards or load centers, are the distribution points for electrical circuits. The panel contains circuit breakers or fuses that protect the individual circuits. The panel must be properly sized to accommodate the anticipated load and provide adequate space for future expansion. The NEC requires that the panel be listed and labeled, and it must be installed in a readily accessible location. The panel must also be properly grounded and bonded to ensure safety. Wiring methods refer to the techniques and materials used to install electrical conductors. The NEC specifies the approved wiring methods for different applications. Common wiring methods include non-metallic sheath cable, NM cable, electrical metallic tubing, and rigid metal conduit, RMC, and flexible metal conduit, FMC. The choice of wiring method depends on factors such as the environment, the type of construction, and the local codes and regulations. Conductors must be protected from physical damage and must be properly supported and secured. Electrical boxes are used to enclose and protect electrical connections, such as splices, terminations, and devices. The NEC specifies the types of electrical boxes that are approved for different applications. Electrical boxes must be properly sized to accommodate the number of conductors and devices contained within them. The boxes must be securely mounted and must provide adequate access for maintenance and inspection. Receptacles, also known as outlets, are the points where electrical power is drawn for appliances, tools, and other equipment. Receptacles must be properly installed and grounded to ensure safety. The NEC specifies the types of receptacles that are approved for different applications, such as general-purpose receptacles, ground fault circuit interrupter, GFCI receptacles, and arc fault circuit interrupter, FSI receptacles. GFCI receptacles are required in wet locations such as bathrooms, kitchens, and outdoor areas to protect against electrical shock hazards. SI receptacles are required in bedrooms and other areas to protect against arc faults, which can cause fires. Lighting is an essential part of any electrical system. The NEC specifies the requirements for lighting installations, including the type of fixtures, the location of fixtures, and the control of fixtures. Lighting fixtures must be properly installed and grounded to ensure safety. Energy-efficient lighting, such as LED lighting, can significantly reduce energy consumption and save money. Controls, such as switches, dimmers, and occupancy sensors, can be used to control lighting and reduce energy waste. Safety is the most important consideration when working with electrical systems. Always follow the NEC and other applicable codes and regulations. Energize circuits before working on them. Use appropriate personal protective equipment, such as gloves, safety glasses, and insulated tools. If you are not qualified to perform electrical work, hire a licensed electrician. Regular inspections and maintenance are essential to ensure the safety and reliability of electrical systems. Inspect wiring devices and equipment for damage and wear. Test GFCI receptacles regularly. Replace worn or damaged components promptly. Keep electrical panels and equipment clean and free of obstructions. By following these guidelines, you can ensure the safe and efficient operation of your electrical systems. Remember, when in doubt, consult with a qualified electrician to ensure that all work is performed in accordance with the applicable codes and regulations. Properly sizing a neutral involves several critical steps, primarily based on the expected loads and applicable electrical codes. The National Electrical Code, NEC, provides specific guidelines to ensure safety and proper operation. It's important to understand that the neutral conductor carries the imbalance of current between the phase conductors in a 3-wire, single-phase system or a 4-wire, 3-phase system. First, assess the loads connected to the system. This includes lighting, motors, and any other electrical devices. Identify the type of loads, whether they are linear or non-linear. Linear loads, such as incandescent lights and resistive heaters, draw current in a sinusoidal waveform, while nonlinear loads, like electronic devices with switching power supplies, draw current in a non-sinusoidal waveform. Nonlinear loads generate harmonic currents, which can significantly affect the neutral current. Next, calculate the current for each phase conductor. For a single-phase system, this involves determining the total amperage drawn by all devices connected to each leg of the circuit. For a 3-phase system, calculate the current for each of the 3 phases. Ensure that you account for the demand factors, which allow for a reduction in the calculated load based on the likelihood that not all devices will operate at their maximum load simultaneously. Demand factors are typically specified in the NEC based on the type of load and the number of devices. Now, determine the imbalance in current between the phases. In a balanced system, the current in each phase is equal, and the neutral current is 0. However, in a typical electrical system, the loads are not perfectly balanced, resulting in a neutral current. For a single-phase system, the neutral current is the difference between the current and the 2-phase conductors. For a 3-phase system, the neutral current can be calculated using vector addition, taking into account the phase angles between the currents. It is essential to consider harmonic currents, especially in systems with a significant number of nonlinear loads. Harmonic currents can cause the neutral current to exceed the phase current, requiring a larger neutral conductor. The NEC requires that the neutral conductor be sized to carry the maximum unbalanced load. For systems with primarily linear loads, the neutral conductor is typically sized no smaller than the phase conductors. However, for systems with a significant amount of nonlinear loads, the neutral conductor may need to be sized larger than the phase conductors to accommodate the harmonic currents. Consult NEC section 220.61 for specific requirements on neutral conductor sizing. In addition to the calculated load, consider any future expansion or changes in the electrical system. It is often prudent to size the neutral conductor slightly larger than the calculated load to accommodate future needs. This can save time and money in the long run, as it avoids the need to replace the neutral conductor if the load increases. Also, remember to consider the voltage drop in the neutral conductor. Excessive voltage drop can cause equipment malfunction and reduce the overall efficiency of the system. The NEC recommends limiting voltage drop to no more than 3% for branch circuits and 5% for feeders. To minimize voltage drop, use a larger conductor size or shorten the length of the conductor. Furthermore, consider the environmental conditions in which the neutral conductor will be installed. Factors such as temperature, moisture, and corrosive substances can affect the performance and lifespan of the conductor. Choose a conductor with appropriate insulation and protection for the specific environment. Conductors installed in hot environments, for example, may require a high temperature rating. Remember that proper grounding and bonding are essential for safety and to prevent electrical shock hazards. The grounding system provides a low impedance path for fault current to return to the source, allowing the overcurrent protection devices to quickly clear the fault. Ensure that the grounding and bonding conductors are properly sized and installed in accordance with the NEC requirements. Finally, document all calculations and decisions related to neutral conductor sizing. This documentation can be helpful for future reference and can also be required for inspections and permitting. It is always a good idea to consult with a qualified electrician or electrical engineer to ensure that the neutral conductor is properly sized and installed in accordance with all applicable codes and regulations. They can provide valuable expertise and guidance, helping to ensure the safety and reliability of the electrical system. Understanding these concepts will allow someone to design the correct neutral for the application. These steps are essential to guarantee the performance and protection of the system.